All right, hi everyone, and welcome to another ISI Natural Language Seminar. We're very excited to have Skyler Hallinan here with us today. He is a PhD student in computer science at the University of Southern California, where he's advised by Sean Wren. His research aims to build trustworthy AI systems with robust reasoning capabilities via data-centric approaches. His work spans three core areas: understanding how data impacts downstream model behavior, safeguarding user data and privacy, and advancing model capabilities with better data. Previously, he was a research intern at Apple and Amazon and received a BSMS in computer science from the University of Washington, where he was advised by Yejit Choi. Quickly, this is our second to last NL seminar of the semester, so we will have one virtually next week, and then after that we will be done for the semester. So please welcome Skyler for his talk on the surprising effectiveness of membership inference with simple n-gram coverage.
Yeah. So much for the introduction. Yeah, I'm very excited to be able to chat here. So this is some of my most recent work. As you will see in the top right, we just submitted this. So yeah, best case we'll be able to get in, but I still think this is a super interesting project with a lot of collaborators that I'm really happy to share with you. Okay, let's get started. So let's set the stage. So what do we know about large language models, and how is this related to our overall talk? So as we know, there's kind of been this advent or this rise of large language models, or maybe you can call it as people kind of consuming them more or becoming used to them. But what we know is they're extremely capable, and they're used in many consumer-facing applications. And another fact about language models that we know is a large amount of their capabilities come from their data. So there's this natural issue where lots of people are currently using large language models in consumer-facing areas. A lot of their capabilities come from their data. What happens if their data contains sensitive or otherwise vulnerable information, like copyrighted information? We might have, this is an example, we might have conversations like this, where a user asks, can you please tell me a story? And in this case, the language model starts to output this string, which, if you can recognize, is from Harry Potter. And this is a very special case because this is verbatim. You can easily recognize that this is from Harry Potter, or us humans can easily recognize that. We also have other verbatim response examples which are unideal or not ideal. For example, inadvertent leakage of other sensitive information. So maybe I want to know what is a typical format of a medical record so I can do my own thing. And now the language model does give me the format. I gave a harmless query, but it's giving me information which the user did not consent to, since this data was part of the training. And then finally, you can think of an extreme case of this, where these vulnerabilities can also be intentionally exploited with malicious queries. So now we're not just saying, give me what does this format look like. Now we're intentionally saying, give me some like OpenAI API keys. So of course, like, there probably will be a little bit more complex of a prompt to elicit this behavior. The jailbreaking won't be so easily, but the fact that this kind of capability exists is what makes some of these jailbreaks very effective. Otherwise, if it doesn't really store this information, then there's no point to try to take these API keys. Otherwise, your guess is as good as random. And also, I should note, this is a randomly generated API key. This is not real sensitive information. Yeah. If you guys are going to go back to the recording later. Okay. Okay. So what has this culminated in? I have these very, intense graphics, but I'm trying to set the stage where this is kind of a real world issue. So here are two explicit recent cases where different news articles are suing model providers for training on their copyrighted work. And essentially they're asserting, not only are you training on our copyrighted work, you're diminishing the utility of our own text, because people can use a language model rather than paying to read our articles. I can ask, okay, well, I don't know specifically like the article off the top of my head, which they cite that they're trained on, but the summary is that people can kind of access these without any attribution or credit, and kind of diminish the utility of these actual news articles. So this kind of motivates some what I will go into next in this copyright claims. So ideally we want companies to have accountability for the type of data they're training on. So the title says copyright claims, but of course this applies to all the other sensitive information I mentioned. So we want them to have this type of some kind of accountability. But if you think about a lot of the large language models current releases, they're going to tell you a lot about how they train their model, how many parameters they have, etc. But there's still one part of the pipeline which is very protected, which is data. That seems to be something super protected, and that's kind of, if you read any model releases, that's where it's going to be very hidden. So I mentioned this because all of this information, everything I've said, naturally motivates membership inference attacks, which I'll define on the next slide. So, for example, we might have a conversation where I, as a friend or a lawyer, say, I think you've trained on my client's copyrighted data, and I see some effects, and the model provider can can flip it around and say, prove it. And that's what is motivating these membership inference attacks. So what is membership inference? I've given you a lot of background on this, all these verbatim examples, but let's take a step back and think of what this is. So membership inference, which some people have also deemed like copyright detection, although membership inference is the term that's normally used, aims to find, we have some language model, which we denote M sub theta. We have a corpus C, which consists of text documents. So can we determine which, if any, documents in this corpus were used in the training of M sub theta? And so an attack, a membership inference attack, is a method which tries to determine this. Okay, so I set the stage for the task. I'll now talk about some of the previous work and why there was a gap for us to fill. So the previous work is based on loss-based methods primarily. So there's this 2018 paper, which is essentially saying, can we determine the membership of a sample by computing the loss? So if we have this very simple function, which is we're going to look at the loss of some sample X under our model. We're going to use that as a signal with the intuition. Yeah.
No, not for you.
Okay, cool. So the intuition is if I've trained on this sample and I've optimized it for it, then the loss is going to be lower. So that's a pretty easy to understand baseline. We also have this follow-up to this idea from Carlini in 2020, which is how does the loss of a sample on our model M sub theta compared to the loss from a reference model M sub R. And so the intuition behind this is we're going to assume that our reference model is kind of a smaller general purpose language model, which has less or diminished memorization capabilities. That's kind of just a field kind of assumption that people make, which is this is just going to be a general purpose language model, which is smaller, so it doesn't memorize. And we normalize by this to kind of account for the fact that X itself might have a lower or higher loss due to the perplexity of the sequence itself, rather than the fact that the model has memorized it. So we're trying to remove this confounding factor, and we're going to be like normalizing by, okay, in general, what's kind of the perplexity or the surprisal of this sequence X. And there's also another paper, which I don't have here, but it does a similar thing of doing this reference model, but rather than grounding on the loss from this M sub R, you use the compressed size of the file using this library called zlib. So that's kind of trying to measure a similar thing.
Sorry, could you explain again why using the reference model?
Yeah. So the 2018 case, this works well in practice, but it has this assumption that if I have a low loss on a sample, this means my model has more likely been trained on that. But there's this confounding factor, which is that what if this sequence just has lower surprisal in general? The sequence might, if you do a bunch of language modeling and you kind of learn language patterns, there might just be sequences which on aggregate kind of have a lower surprisal. Especially once you start getting into like different length factors and calculating complexity for a very long sequence, you might have these confounders where you don't really know if a low or high loss is only due to memorization or also because of the sequence itself. So how do we solve this? So M sub R, hopefully the assumption is that it shouldn't have the same memorization, So we're trying to explicitly account for this factor where, okay, normally, the surprisal of this sequence is this, but under our target language model, now the surprisal is this. So if the surprisal is much lower than what we would expect from a general purpose language model, then it's likely to be a member. So yeah, thanks for clarifying.
So the model can be like inference.
Yeah, it can be. I think in practice, usually people are using more on like the 1B scale model, I guess, if you're benchmarking like 7B and up. But yeah, usually more in like at least the GPT-2 scale size, like GPT-2 small, like 350 or 150 and up million parameters and up. But yeah, there's a lot of some previous work which is looking into the reference model. But it definitely is helpful. As I'll show it as a baseline. So. Okay. And then there's also this previous work, which again is based on some part of this like output distribution with respect to a specific text. So this is based on the logits rather than the actual loss. This is called min k percentage. So how does this work in general? You're going to, rather than look at the likelihood of all the tokens of the sequence, you're going to look at the likelihood and take the average of the k% most unlikely tokens from a candidate member. So the idea is, if I have a sequence which I'm not sure if it's a member, X, which is a candidate member, if it really is a member, even the lowest likelihood tokens in X will have a high likelihood in this model. So how does this differ from the loss or the reference loss? If you imagine like, for this sequence which we have, like the 15th Miss Universe Thailand pageant was held at this Royal Paragon Hall. If you're looking at all the tokens, like the word held and at, just from language modeling in general, are going to have very low, like those are going to be the most likely target tokens, regardless of whether I really trained on this. The tokens which have a very like high surprisal might be more meaningful to check for. So we're kind of somewhat similar to, I guess, the similarity to the previous slide is that we're just trying to account for generally familiar tokens. Okay, so these sound like 2 or 3 very strong baselines, but why are they not always feasible? AKA, what is the motivation for this work? So if you notice, the previous baselines assume white box access to the model. We need to know the loss of the model on a sequence, or we need to know the probability distribution over the sequence. So if we think of like, these are 2 examples of some popular models which provide limited access to what they return in response to user queries. So this is like ChatGPT and Anthropic, for example, Claude. So in this case, you don't actually have access to these log probabilities or loss, which means you can't run any of these attacks on them. So actually, like ChatGPT used to provide some of the log probabilities on the prompt side, but they kind of rolled back, presumably due to some kind of extraction vulnerabilities from some previous security work. But the kind of final summary of this is that what we can assume from these is that we only have black box output access. So that means essentially we can function only with text outputs. Okay.
So are you assuming here that you only have text outputs, that you don't have like any token probabilities for the output text?
Yes, that's a great point. So yes, in the models, you do also get the output text probabilities of like what you mentioned. None of the baselines actually use this. We considered using this for our method as well, but we wanted something like agnostic of in the future, like what if that doesn't exist anymore? But yeah, that's a good point. So a method presumably could do something with that. Okay, but I guess, yeah, the most important thing which they took away was like the prompt token probabilities. So you could just run in your entire input. Okay, so now we have this question, we have this motivation, and we have this question. So how do we construct an attack that uses solely text outputs? So we have this key intuition, which we assert or claim. So models are more likely to memorize and subsequently generate text patterns that were commonly observed in their training data. So if you think of what are the loss-based methods trying to capture, they're trying to capture what is encoded in your model via this loss. And now we have this restriction where we can't access this anymore. So we have this and condition where hopefully they can subsequently generate these text patterns, which are also encoded in their parameters. So we have this, and how can we actually utilize this information? So I will introduce our method. So our method, we deem n-gram coverage attack. At a high level, again, so we're trying to understand, was this model trained on some input X? And our high level approach is to approximate how M sub data has memorized this sequence by empirically measuring how well the model sampled outputs align with that sequence. So what does that mean? So we're going to prompt our model multiple times with a prefix of X, and we're going to measure how well can the model reconstruct the rest of X, which it hasn't seen before. So I have it written down, naturally regenerating the remaining suffix of X. And again, we have this intuition where we're trying to fill in for the loss of it, no pun intended, but the loss of information, which we don't have from the loss baselines. And we have this intuition that models trained on some data have a chance of repeating it. That's kind of the core idea in this work. So I'll go more concretely into the method now. So we have it written up as an algorithm. So again, these are just what it requires and what it outputs. So we have our target model, we have our input text X, and we're also going to define a couple other parameters, which we're going to use later on. So we have some threshold that's going to be to actually make our decision. We're going to get a score, and if it's above this threshold, we'll say it's a member or less. And then these other hyperparameters or other kind of things I'll introduce as we go on. So our first step, like I mentioned, is we're going to sample D generations from our model using part of X as the prompt. So right now we have X up to the kth token. That's what this notation denotes. And we're going to do that D times, and we're going to get a set of these generations.
Generate, oh, meaning you generate.
Yeah, yeah.
Not over time, right?
Yeah. Now we have these generations, and we're going to compute the similarity of them to the rest of X, which wasn't seen before. So that's this greater than K symbol for all of our generations. Finally, we have a bunch of similarities. So let's say like some of the texts were very similar, they reconstructed it well, but some of them didn't. We need to figure out what's the way to condense this into a single score so we can make a prediction. So we're going to use an aggregation function. I'll go over kind of more engineering details on what we can use here, but I just want to keep it abstract. But we have an aggregation function that can condense this into a single scalar value. And then, like I alluded to earlier, now we'll use this epsilon parameter to predict member if this aggregated scalar is greater. Otherwise, we're going to predict that this is not a member. Yes.
Do like a known ground truth, like
Yes. Yes, that's actually there is a known ground truth, but the kind of scope of data sets which you can use is kind of limited. If you think about like what people know about OpenAI's training data and if they've actually ever like confirmed anything, it's a bit limited. So I'll go into a little bit of that on the like data set side, but yes, there are some ground truths we can use. Yeah, exactly.
So I have a clarification question. So are you taking like, so K is fixed here. You're not, in a sentence like I have a dog, you're not saying I and then generate next, I have and then generate next. That's
a good point. We fixed K, but yeah, that's a good point. You could presumably like change like the context, and then you could do ensembling over those similarities, right? Or even do like a weighted similarity. Like if I'm only going to be generating like the last token, presumably like 100% match of the last token is less meaningful than if you get 100% match on like 50% of the tokens, like if I generate using half the context. So yeah, you could maybe do something like with like a weighted kind of aggregation if you have those similarities. But yeah, that's a good point. You could do something with different context lengths. For now, we're just doing 1K. but generating multiple times.
This model is like this framework is agnostic to the decoding that the MTSL is doing. Like either is gradient
Yes.
beam search.
Yes.
So this is,
Yes, that's a great point. It is agnostic. We found that using nucleus sampling, so you want to do some kind of sampling.
Yeah.
That's kind of where you get the benefit of this work. I'll have it on one of the next slides, but if you think about how likely it is to get a very high overlap match, given like that it's like 20 or 30 tokens, it's very unlikely to do that by random chance. So if you get like one hit that's very high, then that's a very good sign. So sampling is definitely really important. We did a little bit of ablations, which I'll mention. We did on the temperature, but we might need to do more on maybe like the top T parameter. But yeah, I think like that's a very important part is how you actually get the, yeah, because a lot of memorization work also has this assumption where we're going to do some like greedy decoding because that's kind of the best representation of like the models with respect to some sample. But actually this work is kind of nice because it shows like you can actually kind of try to reconstruct the distribution by sampling many times and hopefully try to empirically estimate what does the internal representation look like or what the internal like, yeah.
So I have a related question.
Sure.
How well, so let's say we've got an underlying language model,
Yes.
and then we have some sort of RLHF or instruction tuning or even like safety guardrails on top of it that are post hoc changing the distribution. Is this method able to like see through that to get out what data is in the underlying language model?
That's a great point. So yeah, so I guess like those kind of post-training safety measures, some of them are actually explicitly designed to prevent some of this verbatim repetition. So that is a struggle. So in some cases, this is like an issue. So one of the data sets which like the OpenAI is actively like trying to prevent people from generating is like the New York Times articles, which were kind of listed in the lawsuit. But I guess one thing we did was we kind of explored with a variety of prompts just to see like what is the best we can get without refusal. So OpenAI models will generally refuse if you explicitly ask it to, one, generate something verbatim, and two, from existing work. Something you can get around that is if you just give like the text itself and just ask it to generate the rest. It wouldn't like not in that case. So this is just anecdotally, but what we noticed in that time is that it wouldn't necessarily refuse as much as if you say like, you know, this text, generate it verbatim, like the generate verbatim if you do know it. Then it's sometimes like, oh, I will not really do that request because that doesn't abide by my guidelines. But yeah, that's a good point. I think if you do want to kind of circumvent some of these content regulations, then simple prompting where you don't necessarily like ask for these very fine restrictive like verbatim stuff still works, which we found. But yeah, that's a good point. I think the knowledge is definitely still encoded. There's some like interesting cases where if you ask it to generate text verbatim, it'll like, let's say like the Harry Potter example, if I ask it to generate the text verbatim, it'll say like, sorry, I cannot generate the rest of Harry Potter. So you can definitely tell that there is some internal knowledge. At the same time, I did notice like playing around in the playground of like OpenAI is that there's some cases where it deems that even though the work is still under copyright law, it deems that the work is famous enough that it'll still give a large part as just an output. So for example, I was playing around with different famous books, which are still copyrighted, and it was still able to like generate some of those. Usually the first section though, it kind of loses its ability the more later you go through. I'll give a walkthrough of an example, and then maybe we can, I'll go into experiments after that. Oh yeah, actually, before the example, what are some of the similarity metrics
Okay.
we can use?
Adam, are you trying to ask a question?
Okay, I'll continue.
We do have a question in Zoom
Oh,
chat.
cool.
I'm not sure if it's the same question that was trying to unmute. But Harsha Varden Alini says, hi, quick question. In the Ingram coverage attack algorithm, how can we decide on what part of X will be used as the prompt? If the considered prompt itself has a very important copyright information and later suffix part is not much essence, any comments on how these kind of scenarios will be handled
Yeah,
for this algorithm?
yeah, that's a great point. So we didn't consider this case where you have like where X itself is composed of like different levels of kind of security or privacy. So that's something that's interesting where you could kind of like look for where is the best place to split. So we have a very naive approach where we're basically saying we're just going to split at like the 50% border. So K is kind of dynamic based on the actual input. So like maybe like I wouldn't just use the 50th token if my string is only like 60 tokens. I would use like 30, for example, if we're doing 50%. But yeah, I guess for these cases where maybe the content of the X itself matters, then maybe we would want to have some like smarter way to ensure the splitting. Okay, so and I can talk a little bit more about that later. I do have some comments about that, but I'll just go through this first. So what are some of these similarity metrics we use? So I think a key part which I want to emphasize in this work is that the similarity metrics we use are 3 different n-gram overlap metrics. So what does that mean? They're very interpretable, unlike like an embedding-based similarity. They're also super efficient to compute. So you can see where the matches are happening, and you can do it pretty quickly. So what are the 3 ways we're doing this? So one is called coverage. So this is quantifying the overlap between 2 documents by computing the proportion of tokens in X2 covered by matching n-grams of at least length from X1. So I'll have like an equation if anyone wants to just read it, get into the details. But and essentially, and I'll show this visualization on the next slide, we're going to see how much of the tokens overlap in matching n-grams and count those, and we'll get a score from 0 to 1 saying X% of tokens are covered by my reference document.
Is this L like a tunable parameter?
Yes, exactly. Great question.
What about just like root L or something like that?
So we have a way, like something similar to have this like alternative measurement, which is just doing like the longest common substring. But yeah, that's a valid point as well. Okay. So we also have this metric called creativity index, which is on this parameter which Katie alluded to, where we're going to increase the n-gram sizes iteratively. So so you see we have this L where we're going to look at the matching n-grams. So we're going to iteratively increase this and then sum up the coverage. So this creativity index is from another paper, and the idea behind this is a higher creativity means more uniqueness. So in practice, we're going to use like the negative of this because higher means like more creative. I guess if people are confused, I'll try to show a visualization on the next slide to help alleviate this.
Reward in what sense, I guess, is the question. You say reward.
Yes. Rewarding meaning giving higher scores to.
And the higher score means it is
more creative.
meaning less overlap.
Yeah, less overlap. So yeah, this is from, I think I have the citation on the next slide, but yeah, this is from another paper. So this is, they're like building on this coverage metric. In this paper, they're introducing this creativity index as like a way to assess like linguistic surface form creativity. Okay, and then finally, yeah, so what the equation looks like. Then we also have this maybe more simple baseline, which is we're going to take the length of the longest contiguous substring between X1 and X2 and compute the length. So just in case it's helpful, yeah, I guess it's slightly blurry, but let's say we have this like generation from Llama 2, where it starts with a sickening thumb and then ends with closed. So the red areas indicate where there's a match with the reference text. So if we wanted to take the coverage, even though there's multiple overlapping spans, we would count the number of tokens which exist in at least one of these red spans and divide by the total number of tokens, and they'll give us a coverage score between 0 and 1. And if you want to intuitively think of what is the creativity index doing over this, it could be the case, like let's say we have a case where all the matches are 1 token long and our minimum L is 1. So even though the coverage is 1, now let's also consider a case where both of our matches, we have also another coverage 1 example, but the matches are like both of these paragraphs. So if you want to reward longer matches, you can use this creativity index, which is going to increment the L. So once you hit 2, the first example, which is all 1 gram matches, is not going to have any contribution anymore. Whereas the one that's composed of 50 gram matches is going to continue to have this contribution until you get to L equals 50. That's kind of the intuition of this creativity index. Okay. And then finally, we also have this question, which I alluded to: how do we aggregate the similarities of multiple generations to the ground truth suffix? So we have like 4 basic functions which we're considering: max, min, mean, median. We did some exploratory work and like doing maybe training a classifier on these, but we found the performance is good enough using like these existing functions. And in practice, we find that doing the max works the best. So the analogy I like, or analogy that I found, or hopefully makes some of this intuition phrased in a different way, is like something like a lock and a key. So if you randomly try to generate a key to fit a lock, you're going to have a very low success rate. But if you have the actual key, that's going to be both low probability, and if you make it in, then you know that you have the right one. So similarly, if I am generating the rest of text sequence and reconstructing the suffix, and my match is very strong, that's going to be a very strong signal. It's going to be very low likelihood of a false positive. Okay, now I'll just quickly go through an example of how this works, just maybe it's helpful for people. So let's say we have this candidate member. This is from Dorian Gray, a famous book. So we're going to split this into 2 sections, a prefix and a suffix, which are denoted in these 2 colors. That's step 1. Now, step 2, we're going to use this as our input to our language model. We're going to sample multiple generations. And these are all real, by the way. These are from GPT-4o. Okay, so we're going to obtain D completions. In this case, D equals 3. Now, we're going to bring back our suffix, and now we're going to compute our n-gram coverage metrics. So we're going to compute our n-gram overlap. So for example, we have this exact string match your extraordinary. Oh, I guess should stop at extraordinary since it's missing good, but it's basically that small snippet. This one also has your extraordinary and will not be able to do. And then finally, this one's also your extraordinary, will not be able to, and then achieve. So only differs at the end. So once we do all these, so this is, of course, the coverage case. This is not creativity index or longest common substring. We'll get these different scores like, okay, this one's around 43%, this is around 89, this is 77% coverage. Now we can say something like, on average, the model's generation has an n-gram coverage with the ground truth text of 70%. So we have these 2 options, and we're going to say it's likely a member. Of course, like this is based on some threshold which we're going to set. So 70% doesn't always entail member. It's just for the example. Okay, so finally, before I go into experiments, I want to mention one last baseline, just because there's one other work which does black box MIA. I just want to convince you why our work maybe is better. I was trying to think of a good way to say that. So, yeah. So I'll just like iteratively go through. So this is their method figure. So how does their method just work as a whole? You have a passage where you don't know if it's a member or not. So the first stage is to paraphrase it. So you have your original passage, that's your candidate member. I'm going to paraphrase it and get 3 paraphrases. So these are 3 different model generated paraphrases. Now I'm going to supply these 4 passages to my target model as a multiple choice format and say, of these passages, which is most likely to be the real book from The Lord of the Rings. And then, as you see by these dots, I'm going to do this for every single permutation so that we remove any bias of position. So that ends up being 24 permutations. And then I'll get the score out of 24. How many did I accurately assess? If my score is very high, presumably I've seen this book before because I can correctly identify it regardless of the position. I know which is the correct written one. Otherwise, maybe it hasn't really been trained before if it's about random. So that's this baseline. And I'll just quickly go through, this is one of the downsides of this black box. If we have a candidate member which has been tokens, you can kind of quickly see that this becomes expensive. So you have this paraphrasing pipeline and then like 24 multiple choice QA. So this incurs a total token budget of around 100 N for one inference. So already you see like, I mean, a large part is coming from 24 times 4N in the multiple choice step. That's already 96 N. And then you have like a paraphrasing part, which also requires access to a more powerful model. Like in this case, this paper is using Claude as their paraphrasing. And then like our method, why is this more manageable? So we can actually have some constraints to constrain our generation to be exactly the amount of tokens which is removed. So when we generate, we're going to only generate exactly how many tokens are in the suffix. So then our total token budget becomes D times N. So as long as our D is kind of a reasonable size, it's kind of going to be more computationally efficient. And then like we also empirically tested this out as well. And besides like these like theoretical numbers, decomp is also running a lot slower than our method.
I think the last 2 words are the ones that would be the most justifying to me.
Gotcha.
So let's see.
Okay, cool. Yeah.
So you talked about what data you use. I'm curious, like we use their data and like you said it performed worse. Like
yeah, great.
Like correlates in terms of what they think is actually trained on.
Yeah, that's a good point. I haven't. Yeah, I guess. Yeah, I wanted to put this like runtime here, but also have the benefits. So actually, yeah, I didn't describe any results yet, but I'll get to that. That's a good point. Yeah.
If I can, I guess like give maybe a small suggestion. To me, it also seems really important that your method doesn't rely on verifiably clean data. Because if we're trying to like reverse engineer what's in GPT-4, I don't know, I'm suspicious of like they have this data that they know is clean.
Yeah.
And you know, even if they say, well, this book was published after after the model's knowledge cutoff, it's like, do you know beyond a shadow of a doubt that no version of that book was online before?
Mm-hmm.
You talking about the decomp method?
Yeah, the decomp method.
There's a dependence on clean data.
So they have this in their figure 1 where they
ask for this like that. What's it called?
Yeah, I think I know which paper.
No.
Oh, okay.
Sorry. So you should go.
Yeah, that's a good point.
So
when we actually run the baseline, we remove this assumption. Like we remove this part, which is so this part where they're doing this clean data is for calibration for the positions, but we actually didn't like run that. But yeah, that's a great point too. Like I think that's a good point.
Yeah, I mean, I think it's something that you should definitely put in your advantages slide.
Yeah.
Like we don't have this
Yes.
dependency.
Yeah.
Wait. What do you mean by calibration for positions?
Okay, so
You mean like where you start generating more text?
So like they have a section where they want to see like even if I have some like ground truth clean data, and I change like the order of the like data in my permutation, how much does the like correct response differ from like the expected, like basically trying to see what the weight of the ground truth answers are, and then they'll do some like step where they're subtracting based on the position bias. But that's something I actually didn't like. They also didn't have this in their code, so I didn't like re-implement that. But yeah, I think the assumption is not great as well. Yeah, I'll try to continue. Okay, so I'll briefly just go through what did we actually run on. So kind of three main ones. So one is this like open weight models. So in some sense, we're constrained by like what models we can use based on what data sets are already available. So it happens to be that the data sets which people have previously been using for MIA work on Llama 1, this Wiki MIA data set and this book MIA data set. So we also have these like closed API access models, which people haven't really studied before. I think that's a great contribution of our work. Then finally, another interesting direction where we explored this in new to our work is looking at this instruction tune models, where we have a base model and we're going to fine tune our data. So does membership inference still work in the fine tuning case? So that's also something unique we're doing. And then what are the actual data sets for these models? So one is this like Wiki MIA data set. So I think like as Katie alluded to, you do have issues in a lot of existing MIA sets, given that they are temporally separated. So Wiki MIA and Book MIA are kind of what we're stuck with in terms of what people are using to benchmark. What I did to alleviate this is hopefully like looking at two new data sets, which will give more insight. So Wiki MIA 2024 hard is something we construct where we are trying to address two issues. So Wiki MIA has a cutoff date in 2023, so you can't really benchmark any of the new OpenAI models because they have a cutoff date that's overlapping. So one is we're looking at 2024 articles. Another thing is if you look at Wiki MIA, it's articles written before and after a certain date. So you have this issue where articles can often be related to a date which took place in a specific year. So you can kind of have these shortcut signals to determine if something is a member or not. Something we're trying to do to address this is we're now making members and non-members the same Wikipedia article, but we're using version history to kind of show they're kind of the same topic, but their content is kind of changing. And then we have some filters to make sure, sometimes a Wikipedia article might change just because someone adds a new paragraph of context. So we have filters to make sure that there's sufficient edits and that the lengths are not too different. So that's kind of our hope of filling in for some of the downsides of this Wiki MIA dataset. And then finally, like I mentioned, we also have this Tulu mix. So Tulu is an instruction tuning dataset itself. So the ground truth instruction data is the member. And then Tulu, the paper, also trains on other instruction tuning data sets, but doesn't actually use them for the final training. So those can be the non-members. And we do a lot of post-processing to make sure that they're kind of as closely distributed as they can be, at least based on the lengths. Okay, and then quickly, how do we actually evaluate membership inference? You can think like, one, you can just set a threshold and get an accuracy, but that's not quite the best thing. We have the following alternative instead. So we have a set of predictions, a scalar set of predictions. We're going to set a threshold, and then we're going to say all values higher are predicted as a positive. So in this case, the member. We're going to get these two metrics, the true positive rate and the false positive rate, and we can plot these against each other. It will look something like this. And then our metric, which we're going to report, is the area under this curve. So it's showing how you can balance true positive and false positive rate as you change your threshold. So this is kind of a more real world use case than just a single threshold accuracy. Okay, so I'll show you a big table first, and then I'll try to distill the results on the next slide. So please don't get overwhelmed by seeing too many numbers. I'll try to give you the main takeaway on the slide after. So this is our results for Wiki MIA. So I should note that this is on the first one that I mentioned, the existing Wiki MIA. And what do our columns indicate? So we have the first four columns are different similarity metrics of our n-gram coverage attack. So COV is coverage. We also have creativity. LCS is longest common substring. And we can do this both the character, which is denoted C, and the word level, this W. And then DC is decop. So that's the other black box baseline.
But these are all AUC numbers.
Yes.
See those metrics.
Yes. Yes. So I guess, I mean, it's also bolded, but something clear is like we're starting with this decop method. I'll go more heavy into the takeaways on the following slide. I just want to show the full scope.
But you guys show like 8% now, all the other
The what?
competitors. categories.
Yes, yes. Yeah, so we have these in gray since it's not necessarily like a fair comparison given the access of information, but it's still nice to know how our method is situated with respect to the other baselines. And you can see it's relatively close. We actually computed the accuracy to be like within above 90% of the average black box baseline, not the best one. So then we also have the rest of the table, which is this wiki MIA part, where we're also, so the performance dropped, which is to be expected because I guess we are making this a harder data set where you have to pick up on these smaller signals between version histories of an article. And in this case, actually, we're performing, in some cases, like better or at the same level of the white box attack, which is very nice. So that's shown by like for example, on Llama 30B, like 0.61 is our best method, and the max performance using this reference loss is 0.61. And I should say, like the baselines are the loss-based method I mentioned, reference loss, zlib, which is grounding with the size of the file, and then this min k. And then random is a random baseline. You just assign it an arbitrary score. So I'll show you one more table, and then I'll go into kind of the takeaways behind these two tables in a more structured format. So finally, we have a much smaller table, which is just looking, this is an existing book MIA data set. And we're looking at 3 different GPT models, the 3.5 instruct, as well as 0125 and 1106. We're kind of constrained on only being able to run on these 3 due to the cutoff dates of book MIA. So hopefully we can address that, hopefully we've addressed being able to run on other stuff with the MIA hard. But again, we're able to perform very strongly, specifically like matching the performance of DCOP and then like surpassing it very strongly on the 3.5 instruct case.
These are much longer segments than the.
Yes, yes.
The average length of the MIA.
So they're all, the wiki MIA are all have a max length of 256. Yeah, I have that computed, but I don't have it off the top of my head. Yeah, books are definitely much longer.
Sure.
Like also like the way they're chunking in this data set is also much longer. Like they're like 512 word snippets. But yeah, that's the right intuition. I don't have the exact number for how much larger books are, but it's definitely much larger. Okay, so what are the takeaways? So takeaway 1, our method n-gram coverage attack performs better than or equal to the black box baseline across all data sets, which is very nice. So like I mentioned, we have this close comparison of book MIA, but you have this like, even on the same data set, you have this fallout for decomp on 3.5 instruct. So why might this baseline be struggling so much outside of this context? And I will note like this book context is the same context as what it evaluated on in their paper. That's what they chose to report, as well as one other like data set about archive papers. So we have this theory, or yeah, this assumption where, so decomp has this assumption that your target model can do 2 tasks at once. You can do faithful question answering, and you can identify like the correct, like what you know to be the correct sequence. So this may not really apply to weaker models where you can follow this like instruction. It's more complex in a sense. So that could be why there's a larger performance drop, especially on the 3.5 instruct model, which has much less like instruction following strengths than maybe some of the newer turbo models. Okay, and then I'll go to takeaway 2. So simple n-gram coverage metrics can perform comparably to white box attacks. So that's a very interesting thing. So again, alluding to this like word surprisingly we have in our paper. So we're performing surprisingly competitive to white box attacks. So if you think of what we're doing, we are just kind of generating multiple outputs and computing the similarities. Whereas the loss-based or white box attacks have so much more information accessible to them. So it is somewhat surprising that we're able to kind of, in a sense, like recover or intuit so much information that we're getting close to the white box performance. So we have further results on 2 other open models, which we don't have in the main paper, just because our method is close to the white box baselines, but all of those numbers are very close to random since these are just like much harder data sets. So it's not a bad thing, it just doesn't tell you much, just all the numbers are close to random. So yeah, I think like this is a nice takeaway where we have this like empirical estimate of a model's memorization and it leads to strong downstream results. Okay, and then I'll just go through this one briefly. I have a couple maybe more interesting slides. So coverage and creativity are kind of consistently outperforming LCS. We maybe have two reasons. They can have multiple matches, so maybe that's obvious. And they're also doing some kind of like length normalization. And then this is a somewhat interesting case, but you also have this balance of coverage versus creativity. In some cases, creativity is actually like worse. We noticed that it kind of varies based on which data set. So for data sets like Book MIA and Tulu, where for books, you have to generate a much longer book. And for Tulu, you need to generate like a long response to an instruction. Where you have these longer generations, like creativity is better at disambiguating when you have kind of partial matches, whereas coverage is better when there's going to be fewer overall span matches. And this is just comes down to a few cases. In general, like their performance is somewhat comparable. These are just some very two small differences. Okay. So finally, I'll go kind of into our interesting like side result, or not side result, but a different kind of approach. So we have this result for Tulu, where we have the coverage and creativity, again, prevailing and being very strong. Again, we have the same takeaway where we're very close to the white box attacks performance, and then we're better than decouple. And then just like the takeaway from this is, it seems like across all different methods, like membership inference on fine-tuned models is something legitimate and something you can extract signal for. So that's kind of something that motivates future work, or something that's pretty interesting. Okay, and then I'll have just 3 more results slides. I know we've kind of had discussions throughout the talk, but I'll try to leave at least like 2 minutes for final questions. So something very interesting we found is, so we did a couple of ablations. So one is we scaled the number of sequences, this D parameter, versus the performance. So if you look at the x-axis here, 10, 20, 50, 100, that's the number of sequences we'll generate to match to a suffix. And then we're going to plot the AUROC on the y-axis with these different metrics that we have. So coverage, creativity, . So a very nice finding we find is that this n-gram coverage attack R method scales with the number of sequences generated. So that gives you hopefully a lot of hope in this method, where you can kind of tune how much am I going to want to spend to try to get this result, and also that it scales well. So I guess the key part of our work is approximating a distribution. So it makes sense once you get more samples, it'll work better.
Is that using max though?
Yes, yeah, that's a great point. This is using max.
Yeah, I mean, once you generate it, right, it's a discovery, right?
Yeah, yes, exactly.
Good.
And then like, how about if you, so this ablation is what proportion of the text works best as a prompt. So if we give the first 25% of the tokens to the second 75%. So now all the parameters are the same, except the x-axis is now the proportion of text as a prompt. And we find actually that near 50% is where the sweet spot is for giving context and assessing the overlap with the suffix. So you have this interesting thing. If you give too little of the prefix, then you don't have as much context to work with, and you risk that your generation won't match the suffix. If you give too much of the suffix, again, this is the fixed budget case. So it will be different if you generate like 512 tokens or whatever. So if you instead give like 75% or 90%, you do benefit from having more context, but now you have fewer tokens to compare against in your suffix, so you have a higher risk of false positives. So it is nice that we see empirically this like 50% portion works best. And then you can see like the findings. Yeah, we also have more findings with respect to like how this relates to min n-grams, as like you were alluding to earlier, but I'll skip that for now. And then finally, this is going back to some of the sampling parameters we just mentioned earlier. How does this scale with generation temperature? So temperature near 1.0 is consistently the best. So you have this like weird balance. You want to kind of surface underlying signals, but you don't want it to be you don't want it to be too out of the ordinary of what the language model will have. So there will be a trade-off between the temperature and the number of samples you generate. So if you generate more samples, maybe you can afford to have actually a lower temperature because you can risk more consistency, and versus if you have fewer samples, then maybe you want kind of a higher temperature. Okay, cool. So that's kind of concludes. I just have a kind of conclusion. So yeah, our method is working well, and yeah, thank you. I'm open to a couple minutes of questions. I tried to squeeze a couple minutes. Yeah.
So you started with lawsuits, so let's go back. How do your tools kind of stand up in court, or kind of go back one step? How does it help?
Yeah.
This new research paper has been approved for use in court.
I have a collaborate, like I have someone who I've been chatting with at USC who has been trying to convince me that you don't need any of this evidence for court because usually it's very arbitrary and decided by like one person who's kind of the expert. I do think it is helpful to, I think something maybe that stands up more to like a general public is also having some kind of confidence metric, like we're like very highly confident. Something nice about like just these type of attacks in general is because you have this AUROC curve, you can say, we're going to choose a threshold where our true positive rate is like, our false positive rate is only 1%. Therefore, everything above this, we're really certain is going to be a match if we say so. So I think it could be helpful, although maybe there's kind of disagreements from other people, but well, hopefully it could be helpful for that. Yeah.
I guess a similar analog to this project is like Getty images suing the future creators. What is it, Stability AI, and but the reason how they're proving is the watermark that's being generated by their images. So I mean, is there a similar strategy that authors can use to have that same watermark?
Yeah, that's a great point. I think what I've seen, and maybe some other people in this room know more about like canaries, but I have seen that you do need a lot of signal in your pre-training data. So I'm not sure if like if I'm like one book out of the thousands that they train on, I'm not sure how much I can influence that if they're, especially for some of the models I mentioned, like Homo and Pythia, where they're training for nearly one epoch. So my data is not really going to be seen that much unless I wrote like a lot of books. But yeah, I guess it is really up to the model providers to kind of themselves be injecting some kind of like signal or canary so that you can later test on. I don't know how much individual can do that injection or like how effective it would be.
You're talking about like paper town or mount lease detection?
Yeah, sorry, I don't know this.
So paper town is a fake town put into a map. People steal maps, and then a mount weasel is a fake entry put into a dictionary. So like if you find those, then like clearly you have to use.
Yeah, something like that.
Is that what you meant? Though?
Yeah,
that kind of watermark.
Yeah.
But I mean, it kind of does, in a way, does that already, right? Like if you generate 50 words and like 75% of those words are overlapped, so like, and then it's creative material.
Right.
Yeah.
So I was wondering a weird scenario where model was trained on text, but it like picks up the general rule in the text instead of the arbitrary engrams that are with that. For example, on math data sets, I would use a 7B model to train a lot of in-house SFT data. But from my inspection, it does not memorize the exact like output COT traces.
Yeah, I think that's a valid concern. Also, with some models like training on paraphrases of verbatim work, like you wouldn't necessarily like see that signal. I think, yeah, that remains an open question. One thing you'll see in a lot of MIA work, and maybe something similar with maybe you have observed, is you definitely see a lot more like memorization signal. I guess sometimes it's inadvertent with the larger models. You can definitely attack them more easily. So one of the reasons why Homo and Pythia models, which we include in the appendix, are in the appendix is because the performance is very poor. Like it does. So on one hand, it is like much harder to extract and like concretely say like you did this, but it's also like kind of like worse as a language model itself. Like people aren't really using that small scale. I think there's also this like interesting open question which I've been thinking about, which is like, is it possible, like, is it ever possible to have generalization without having some memorization? Like, is that going to be something that you pick up along the process as a way to generalize?
Right.
So yes, I think it's kind of a trade-off. Maybe in the smaller model, maybe you would not memorize specific patterns as much, but maybe you wouldn't like work as well generalizing to other cases. So, but you'll definitely see, hopefully, in your case, you'll see more like extractability in the larger model case. But I think there are some countermeasures which model providers are doing, like paraphrasing or doing non-exact training, so that they have like the content or like the underlying content or something without being able to like 100% generate verbatim.
Sorry, a follow-up question, like what is the literature like in this domain where you have the red team doing more advanced paraphrasing?
Yeah, that's something I've recently been thinking about since I just noticed this on like the playground of ChatGPT. Like I was giving it books and it was able to tell me the next part of the book, but in a paraphrased way. So there's something kind of going on. But yeah, I need to look at the literature more to understand how effective that is. Yeah. Yes.
One more question, if I may. So some students use ChatGPT to do their homework, even for programming these days.
Yes.
How will your technology be adapted to plagiarism detection?
Yes. I think so that kind of, there's kind of two questions to that. So one is on recovering like kind of copied like essay content or from other sources. The other one is like a question of machine detection, right? Just like knowing that it's ChatGPT generated. I think, so one thing we didn't benchmark is like math cases. So maybe it is actually harder in the math case, but it's kind of unclear. But I think for any kind of creative writing, what this like creativity index paper found is like, people are always saying like, wow, ChatGPT is becoming very creative. And then maybe students think, oh, I can just copy an essay. But if you do this search with like the reference corpus and you know what the ground truth is, then you can pretty easily detect that it's machine text. So hopefully that is kind of detectable. One limitation of like membership inference is you need to know what is the candidate to look for, right? So if a student submits an essay and I want to determine if this is machine generated or not, if you were to use my method, you would have to kind of know what are some of the candidates of the training text. Whereas the machine detection kind of task, you can do it without any like knowledge of what the training data might be. But I think using our method or other methods, I think hopefully it should be feasible.
All right, are there any other questions?
I'll ask you.